video, we did an example to kind of motivate and give you the idea of Riemann sums, and we only did one of the three possible types. In the last video, once I broke everything up into subintervals, I did what's known as a right sample. What this means is I had divided all of my interval into these tiny subintervals, and whenever I evaluated into my function, I used the right endpoint to evaluate. In general, these look like a plus k delta x, where a is your starting point. So we're looking at the interval a to b. We could also do two other types. We could do a left sample where we do our left endpoint. So once I have my subinterval, I'm going to look at this point. And this one's found by doing a plus k minus 1 delta x. The third one is my midpoint sample. In my midpoint sample, if I have an interval, I'm actually just going to choose the middle of the points. And that one's going to be a plus k minus 1/2 delta t, or delta x. So it doesn't really matter which one of these I pick as long as I stay consistent throughout the problem. And it's important to note that these Riemann sums are just estimates. There are errors with each one of these, and so it really just kind of depends. So let's do some examples of each. Here I have my function, f of x equal to 4x squared plus 3x minus 1. I'm going to use a left-hand sample, and I'm going to use 10 subintervals. And I forgot to mention, we're going to do this over the interval 0 to 1. So the first thing we can find is delta x, and this is always the length of the interval divided by the number of subintervals. So in this case, 0.1. I'm then going to sum between k equal to 1 to 10. I need to know what my function points are, so this is a, which in this case is 0. For left hand, it's a plus k minus 1 delta x. In this case, a is 0 because that's the starting point of my interval. So it's just k minus 1 delta x. So I have 4 k minus 1 delta x squared plus 3 k minus 1 delta x minus 1. And then we multiply the whole thing by delta x. Simplifying is going to give us 4 k squared delta x squared minus 8 k delta x squared plus 4 delta x squared plus 3k delta x minus 3 delta x minus 1 all times delta x. So there's a lot of simplification we can do here. I have these delta x squared, so I'm going to rewrite this. I'm going to go ahead and multiply through by my delta x cubed, 4k squared plus 4. Oh, we had another one too. Minus 8 k plus 4. These two are going to give me a delta x squared 3k minus 3, and then this one is just going to be minus delta x. I can now stick in my value for delta x and use my formulas to solve this. And I'm not going to get an outright number here. I mainly just wanted to set this up and show you how it's done. This time I want to do 0 to 3. I want to do right endpoints and 15 subintervals. Right endpoints look like a plus k delta x. And delta x is always the length of the interval, which in this case is 3, divided by the number of subintervals. So in this case, it's 0.2. So I'm going to add between 15, 1 and 15 of, in this case, a is 0. So I just have k delta x plus 9, all times delta x. Once I simplify this one, I get 12k delta x squared plus 9 delta x. And once again, you can use your formulas and your value for delta x to simplify this. This time, I have the function x squared plus x plus 1. I'm going to look at midpoint, 12 subintervals, and this time I'm going to look from 2 to 5. So midpoint said a plus k minus 1/2 delta x. So my sum is going to be from 1 to 12. In this case, I'm going to substitute in for x. Let's see, a is 2. So I have 2 plus k minus 1/2 delta x squared plus 2 plus k minus 1/2 delta x plus 1 all times delta x. We can simplify this, and this one's going to be a lot more complicated to simplify, but it can be done. We're going to end up with a 4 delta x plus 4 times k1 minus 2 delta x squared plus k minus 1/2 squared delta x cubed plus 2 delta x plus k minus 1/2 delta x squared plus delta x. Like I said, you can really simplify this a lot more before you start doing your summations, but I really just wanted to show you how to set these up.